Hello, Steve Grillo here. This will be Armchair 13, and in this discussion, we will introduce a module that I think will help substantially point to a key part of my argument. As the survey has developed over the years, the key feature was to have us look carefully at Michelson's cross-axis analysis. And in that cross-axis analysis, we had any number of fundamental questions about whether or not there was a lateral inertia component built into it or not. The point being is to parse his argument carefully as his original assay had structured things. He was reciprocating his argument mathematically so that, in fact, there was an apparent ether wind as his beams tried to negotiate the mirror maze he designed. Now, that sounds simple enough. From a mathematical point of view, reciprocating this particular argument isn't a real hurtful thing to the overall analysis. We have found substantial and or at least meaningful other allowances that should be part of the discussion, and that's all we're trying to do here is bring one or two main contingencies to the floor. In other words, one good scientific question should evolve from this, and then I think, as I've tried to resolve in the survey, my own personal assay, a correction can be let, and we can look at a possibility of an experiment that would go a long way to substantiate this total argument. So we look at this particular discussion today with the eye on a module that came together recently as I decided to look closely at what the Galilean rest scenario, and in fact, you'd have to call it the Galilean relative rest scenario, has for us. And of course, the whole point of the discussion I developed, or part of the tool package that I've used, requires us to spatialize the given math that's under discussion. And so if we look here, we see Michelson's original test, his 1887 test. His original test was 1881, slightly same concept, different components. Let's just say less rigorous. But here we see it. We see what I just mentioned. The reciprocation of his argument means that there's an apparent ether wind blowing past, as it were, his fixed entity of his maze. Now, in this particular construct, we actually see two or three key things to his assay. We see that the beam passing through, going straight into the ether wind and returning, returns to P1, and the split beam that goes perpendicular or cross-axis to the system goes out to the mirror and returns also to P1. Both of them emerging along this axis, which, as I continue my discussion, I call this the y-axis, as looks normal to a coordinate system. And here's the key point in Michelson's survey, is that these two, given the actual analytical math that controls this kind of behavior with a given true vector scenario in place, we get this activity, and we see each of these activities producing a distinct time cycle which is not equal. And in that inequality, Michelson thought he could extract a gap, which we see here in this, as the beams are one seeming behind the other on the y-axis, and then collected here in a collector, as it were, to be further processed into an interference pattern. That was his essential assay. We had a long, hard question about what this cross-axis activity should really be about. And today's look at this module will give us, I think, some strong support for at least having a conditional reason or an additional reason to consider that the overall correction I provide may well indeed have a great deal of value. because this seems a little bit stressed in terms of a larger assay where we ask the question, is there lateral inertia involved here? And if it is, then that's surprising because we should be able to see it in other contexts, and we normally do not allow ourselves to see it in other contexts. We are allowed to see it, as it were. We are forced to see it, as it were, by Michelson's assay. Now, we see it most clearly, this lateral inertia, when we unreciprocate Michelson's test. In other words, we now try to show the natural order of things where the test itself, the test proper attached to Earth, is moving through space. And so it's moving through this fixed crystalline, if you want to look at it this way, this crystal overlay of the ether on space itself. And so, well, you see a different context for the behavior. And when we see the different context of the behavior, we see that pretty much the only way it satisfies itself is if we have to impute lateral inertia to that system, or that at least that activity. And it just seems odd, because if you simply re-examine that same cross-axis activity with a non-inertial speculation, which is all we're really trying to say, is one of the analytical pieces here that isn't obviously brought in to be considered, is a non-inertial behavior to the split light beam. And of course, I've reduced things to photons to help us get a clear, simple time-space analysis out of the general set of questions. So if we look at split photons here, we see that Michelson expects them both, after their behaviors through the mirror maze, to return to P1 and exit along the y-axis. Now again, the survey I've produced along the way asks the question, well, shouldn't we maybe consider at least the case where, in fact, the photons do not return at the same spots on this splitter? In other words, P1 itself is simply a point that can be used historically, but as the frame moves, if we again say we are looking at the natural case where the mirror maze is moving through the ether, we see that the non-inertial case we offer provides us with, I think, a special insight. And so to sort of bring the discussion back to a point of departure, what we've always done is try to spatialize Michelson's general math so that we can see what this concept, this possibility of the lateral inertia being native to his argument, but we say probably malconstructed somehow. My main concern following that decision is to simply concentrate on what a non-inertial case would look like and show all the defensible pieces that come into a serial expansion on the idea. And so we sort of leave Michelson's conjectures and his assay kind of aside, his specific maths. We notice that mainly all he was concerned about was the gap between the two, which should show up at this point. The gap was his objective, and not so much a fine critical analysis of the times themselves and the roots of the times themselves, and so on, which I think we have tried to develop along the way more accurately. And this module we're going to look at, I think, helps us a great deal, generate a great deal of high relief on this particular subject. So to help illustrate the concept we're talking about, the spatialization of the mathematical arguments in play, we see this concerning Michelson's assay. We see that if we take the reciprocation out, because there's a good study to be made about an unreciprocated case, or the reciprocated case, but if we take the reciprocation out, we see what we should see naturally, which is a moving source through a fixed ether. That's essentially how we understand the Earth to be moving around the sun on its orbit. It's moving as such through space itself. It's moving. So when we put motion into the assay, we see this spatialization of the cross-axis expression and the on-axis expression. We see the outbound and then return. We see the cross-axis and then return. And as we've noticed, all along, Michelson expects these things to be out of phase when they return, because in fact the mathematical structure is that this case, this spatializing it this way, you get a shorter path to the reflecting mirror and back. This is a shorter path, it's all going at light speed, so it's going faster through its cycle than the on axis, which takes a period to get to this reflection point here, this orange point, and then return back even as the frame continues to move. You get this two legs of the cycle, which take more time to get back to P1. So both of these are returning to P1 by actually passing through this spatial construct for both of them. Well, each of them has their own construct, but particularly the cross-axis crosses this way. Now we see the just the basic L of the frame, the length here represented with this red line. Well, clearly these two sum together to make a longer path than if something had gone straight there and straight back at rest. So for both cases, the L is much shorter than the final path that the photons take as they negotiate a moving frame. So we see that there's an extension, as it were, in time, in the time cycle, even though we're talking about light. So it's that's where the roots of some of this time dilation come from, just right here, literally. Michelson wasn't concerned about the time per se in that larger context. He was only trying to get the he was only trying to isolate the gap, and from the gap he could get his interference. And as we understand, of course, this whole device is floating in mercury, so it could be rotated round and round, as it were, throughout courses of the day, throughout courses of an hour, to produce data about what the interference patterns should be showing him. So that was his larger assay. It was supposed to be a research tool and not a very complicated research tool. This should have been quite easy to put together and have the outcomes almost predictable. You could have probably written the chart of data before you even ran the test. It was so mathematically resolved. And of course, we all learned that the problem happens when he does do the test. He doesn't get these kinds of gaps. Very puzzled. And we know from history, we use we get Fitzgerald's contraction and so forth, and Lorenz's enhancement mathematically. And so we have the Fitzgerald-Lorentz contraction handling this particular problem. Well, we diverted before Michelson, before Fitzgerald and Lorentz. We diverted right here with Michelson, saying, well, why didn't you consider the non-inertial case? The non-inertial case would have been, of course, that it doesn't do this. Because you see, for the photon to split right here and then manage to go to M1 across axis and then back to P1 specifically, well, it has to have some sort of inertia, wouldn't it? A lateral inertia sending the photon down this path and then returning. And that's what we've always brought to bear as the problem. Well, as we matured the argument, we could just see that this probably isn't valid, this imputing of lateral inertia. It just doesn't seem valid. And just look here. We're going to repeat a few cycles of this. This is what it's looking like for Michelson to actually have his original unreciprocated case as the photon leaves its indelible measure, its aspect, into the ether itself as the ether flows by. In essence, the frame or the mirror maze is fixed in space itself as the ether flows by. A bit of a concept that would need discussion, of course, because all along at Michelson's time, the ether was considered an overlay, a special, unique invention, mathematically or at least logistically derived to overlay space itself, which is far too exotic and as it were, so empty that light behaving especially as a wave needs a medium, and so they invented this ether as a medium for light to behave as a wave. And Michelson's test here, in fact, is trying to show some validity or solid validity to this concept of the ether, which is still kind of a speculative argument in 1887, though it's probably a controversial item, like pretty much accepted by some because of its logic, and rejected by others just because of its exotic nature, just being materialized somewhat out of whole cause. The creation of the ether was, in fact, one of the early true empirical constructions that we can see. Just solid reasoning requiring it. It was then just accepted empirically as a potential candidate for how light is maintaining its constant speed through, space. It was the medium constrained light to its one velocity. So that's Michelson's look at the reciprocated case he makes, and how the ether is being perturbed in this very definite V shape, which is part of what his mathematical expression requires. There's his V, inscribed in the flow of the ether, and that's been an important part of his survey, as we see. Leaves P1, returns to P1, even as P1 migrates through space. Now, again, we just jump back to the non-reciprocated case where the movement then is real. And as such, we ask the critical question: how does the photon find this lateral inertia to follow this path through space to return to P1 as it has moved through space? This is where the contentious arguments come together. Now, in the sense that I was trying to bring forward a case for the non-inertial behavior of light, removing the imputed inertia, we see this is pretty much the final case I was able to produce, an animation of what a truly non-inertial case would look like. And it would have interesting propositions built into the final exacting outcome of things. In other words, if the photon coming from down here from the source gets split, but does not put on any kind of angular path to return to P1. You see, call P1 there. Well, P1 moves as it goes, and look where it returns. It returns down south, as in this general context. It returns down south because it only stayed on a non-imputed, or there was no lateral inertia imputed. It just went straight. It was on a path that wasn't diverted by any activity. And again, that's the case we made many times. Or the question we asked many times: how is it being diverted? It shouldn't be diverted. And so just asking this scientific question, what if we look at the non-inertial case? This is merely a scientific question being scrutinized here and then animated. This is just an optional case for the analytics to have resolved some part of the additional case or the expanded case. We just happen to be making it some later time. We see, in fact, that when they emerge, they don't emerge on Y anymore. In fact, they emerge, as it were, time aligned as they are coming downrange now, as if there was no deflection. In other words, not following Michelson's assay, they emerge following a different sequence where now they're abreast of each other, coming towards, let's say, a fixed screen. They will land on the fixed screen simultaneously, but you see the motion of the Earth was supposed to create a gap. And in this survey, we see that a gap does appear, but it doesn't appear on Y, it appears on X, as we looked at the earlier case. So that's the unreciprocated, non-inertial, mathematical and or scientific question that should have power as it goes all the way back to the first moment of this analytical case going awry. And we see this analytical case very simply put forward, and it should have some merit. So we've looked at just a few of the larger renderings of the decades-long survey, and we see this as kind of our final best probable correction for what was going on in Michelson's mirror maze that got him befuddled by no gap appearing. What we've been able to show in a deeper analysis is that really his foundering really comes from the way he presumes that he can tune his mirrors to one spot as part of the setup of his particular test, that if he gets his mirrors tuned to one spot, then he is automatically getting them tuned 90 degrees to one another, as his assay would predict. But we're saying that's exactly where he got it wrong. His assay predicts that the tuning to one spot is valid, and we say it is not. You need to go back to what the test requires, which we say the test is quite valid, but it requires something that Michelson was not doing when he tuned his mirrors. You need to start with 90-degree mirrors and then not have them touched, as it were, to be tuned by a different abstract. Start with 90 degrees, and you may end up seeing that you have 2 points, just as this model in this abstract shows. This is a quick, very fast, and perhaps not so well defended proposition for the case I've made. Of course, I'm just trying to get this survey in to begin to show what the case was about. It was about spatializing the mathematics of Michelson, taking the reciprocation out of his original case, which in itself would have no real foundering attached to it. But then when we take the reciprocation out, we see that we must scratch our heads a bit to sort of ask, well, where does this inertial behavior come from? Because this lateral inertia doesn't fit the natural case where we just see a moving frame through a presumed fixed ether. Something is amiss with this particular idea. Now, we've looked at a few excerpts out of this particular hour-long video in front of the screen here that I think does a very, very useful breakdown of the potentials of the case. It's animated. Some of these details that I just can't expound on at this point, I think are covered well here, but it's its own case and its own article, own discussion that goes into certain key details. And just before we jump into the case that I think needs to be added for additional support for the validity of the case we're making, we look at Michelson's math. We see the on-axis as being described by these of analytics and resulting in a particular summary expression. And then this is the cross-axis breakdown, cross-axis here. And so we see that it mainly varies really only in terms of we've got now a radicand in the denominator where we have no radicand in the denominator here. So we've made the point that this case has more validity to it than this case, and we'll see the how and why of that in 1 second, I do believe. But this is the critique that we ended up making, is that this expression doesn't match what a non-inertial case would do. And now we're going to try to look at exactly how there's a nice fundamental way to say that with some confidence, which then, of course, I think helps the general case very well. What this module and this discussion it really has in front of us is a look at Galilean relativity. And in this case, we're going to spatialize the activity of the inertia as it expresses itself in space. We're going to do that mathematically, and we're going to spatialize it to sort of see what it looks graphically. We're just doing a graphics analysis of what Galilean relativity requires. Now, of course, we have to start with some fundamentals that are, in fact, hinging on the roots of special relativity, but just for the exercise here, we'll try to say it and help move the conversation along. Basically, we start with the idea that an entity or a frame at rest in a Cartesian Cartesian volume or on a plane, as it were, and you have a center point to this particular volume, you can launch a projectile, as it were, and I'm going to be using a tennis cannon, a spring-loaded tennis cannon, where the spring is set under a certain tension. Projectiles under those conditions in a rest frame would just go to the outside or go to the edge or the wall, as it were, and reflect back pretty much at the same speed, and more importantly than anything, at the same time cycles as it goes there and back in each case. Again, we're talking about two separate cases. At rest, the cycle times are the same. And the beauty of Galileo's assessment at his time was that he could notice that mathematically the motion of the frame and its inertial blending of all of its balances shows that even after you move the frame uniformly, and as we know, certain given conditions are just stabilized under some normalcy, you can move it at any given speed, as it were, various speeds, but you still get the same cyclic behavior out of the projectiles going each direction here. That's the notion of relativity that Galileo was trying to put before people, trying to show that the motion of a given frame and all the objects in it are very stabilized, very normed, as it were. But what we'd have to say, though, is if we're going to try to spatialize this activity and look at it at depth, which means, what do we mean by different velocities? Well, we mean moving faster and faster away from a given origin point. See, it has to have an origin point or none of this has any value. Well, we know from relativity, special relativity, that in fact we're actually trying to talk about some absolute origin for which a frame should not have any connection. But we're going to try to make that connection here just to produce this particular case. And so what we see is a special analysis where we will make this frame behave for us as we wish. We will make the tennis cannons behave for us as we wish. The point being is we have to go to this sub-analysis here. We sort of have to say that we've known along the way that what helps the Galilean relativity case work is that mechanical velocities are additive, meaning if the frame has a basic, if the cannon, as it were, the tennis cannon has a 10 kilometer per second motion through space and away from an origin, we'll take that as an origin later, and your spring-loaded cannon under its own specific tension that'll be used in two different cases, it imparts a 20 kilometer per second output. Again, if we looked at it in the rest frame, but now we add it to the moving or the motion or the inertia. Again, this is an inertia study. Add it to the inertia of the frame per se, then we get a total velocity. They are additive. Just like if we were to fire the cannon out of a car that's moving at 10 kilometers per second, it would hit a sign at 30 kilometers per second, even though what we would call the base energy being imparted is 20 kilometers per second. The base inertial component is added to it as well, and so it's 30 kilometers per second. And so we see this activity here. But then we have the case that they are subtractive, because if we had a cannon at the end of the frame or at the wall where the original tennis ball is aimed at, and if that original ball triggers the release of another cannon and projectile out of that cannon, then we see that its 10 kilometer per second motion subtracts from the spring dynamic that's supposed to propel this at 20 kilometers through space, as it were, at rest. So that the net through space, as it were, is only 10 kilometers per second. You see, they're subtractive. And that's the point of this. The cannon is carrying 10 kilometers one direction. The spring tries to impart 20 kilometers worth of energy into such a dynamic, and all that results is a 10 kilometer output. And that's the subtractive component. As they are additive, they are subtractive. And so here's the beautiful point, of course. And the key point to another important resolution of the analytical case, the correction I'm trying to make. The ball, if you actually play the relative rest game, actually sees the cannon separating at 20 kilometers per second. It sees its original 10 plus the 10 it's moving forward at, and the sum is 20 kilometers per second. All seems right in the universe again with respect to the projectile. It seems to be leaving its source at 20 kilometers per second. Quite a phenomenal trick. But of course, what we're trying to bring to bear here is what is inertia really doing in the context of spatialized activity. And the spatialized activity is that it's leaving a point of emission at one resultant while the other component carries on at its resultant, and there's a separation of 10 kilometers each away from that point. Again, space points become very critical throughout this whole assay. You can invalidate them if you'd like, but they seem real if you get serious about it and try to spatialize it. And that's exactly what we're trying to do in this particular graphic here. We see that the first additive behavior is that we have, and here's where we get to the very interesting mathematical approach to what we'll see is interesting down the road here. What we see is that as this is propelled, as it were, at its 20 kilometers with a base velocity of 10 kilometers, we see it trying to approach an entity that's receding at 10 kilometers per second. So it's going 30 kilometers per second trying to overcome a given frame length, which here our frame length is going to be 8 kilometers. It's going to go through this given frame length at its 30 kilometers per second as the frame, or the end point of the frame, the reflection point as it were, is also receding at 10 kilometers per second. So we see that we have to use that mathematically over here in this very basic analytical resolution case over here. But what happens then when we take this into consideration, we get a different return velocity as it comes back this way at a slower velocity, where in fact the frame is approaching it as it has left the reflection point, or where it was triggered to be emitted at 20, but only comes forward at 10 through space. We see this spatial analysis, and we see uniquely, we have to use two different rates to qualify or quantify the inertia properly. We have to use 30 kilometers per second on the outbound journey and 10 kilometers on the return journey. And we've just tried to show how all of this has their own fundamentals in very basic structures. And uniquely, of course, if we take the fact that it took 12 kilometers for this, or the end point was at the 12 kilometer mark away from the origin as this first tennis ball went forward to achieve the wall as the wall was moving, we see that it took 4 tenths of a second. At 30 kilometers per second, it went through the original 8 kilometers of the frame, which is here, 8 kilometers of the frame. Well, the frame, in other words, moved at 10 kilometers per second, a distance that's equivalent, so to speak, in these kinds of matters, equivalent to what it took this tennis ball moving at 30 kilometers a second to reach it. So This is the same x is the same for each uh, problem. X over 10, x over 10, same x. But again, we see the different velocities as roots as being very telling, because this gets us what we want. What we want is equal time to the wall and back to the source. And that's what we get. We get 12 kilometers over 30 equal 4/10 of a second. We get 4 kilometers over 10, giving us 4/10 of a second. So in terms of the timing, the internal cycle time, we get 4/10 of a second for each activity, even though each activity, of course, is running at two different velocities to the same basic L of 8. And that's the root of how this component of Galilean relativity exhibits itself. It went to the wall and came back in exactly the same time. That's what this survey and this spatialization is actually telling you. It went to the wall, it took 4/10 to get to the wall, and it took 4/10 of a second to get back, even though the inertial components are telling you that there were two different velocities through space. And that's, again, the deeper meaning of this assay, is that this is an inertial assay, accounting for internalized components of the inertia itself. Very handy. It would look, if you looked at it, very much like Michelson's original on-axis mathematics. It really will, except there will be a difference, and we'll see that in a second. But that gives us the cross-axis to analyze in this same inertial spatialization. And here we get to a very critical part of it all, because here we're going to see something that also makes perfect sense in terms of an inertial activity. We need to see that the cross-axis activity has to find the photon at a point where its reflection gets back to the original point in the frame. It has to meet two metrics. It has to be exactly at the same point where it was reflected here, and then exactly the same point when it is returned, when it ends and returns here. So both of these journeys have to be 4/10 of a second. If it's 4/10 of a second along this path, it will hit at the same time that it hit here. So if you could build a case in your mind, this is exactly how we get 4/10 of a second here, 4/10 of a second here. We get 4/10 of a second here and 4/10 of a second here. That would balance the Galilean relativity. The balls have gone out and returned. All you have to do now is change the velocity of the base, which is, in our given case here, is 10 kilometers. If you just change this continuously, you continuously get all these numbers different, but this assay remains the same. And so you keep getting a net inertial Galilean relativity outcome. Both the objects, both the tennis balls that are emitted at the same time at t0 hit their respective walls at the same time, and then they reacquire each other back at the original point on the frame. The reacquiring of all things happens at a different point in space, but after exactly equal segments in time. That's how you get the Galilean relativity, is that all these different components are moving at different rates, but they land as you would expect them, as if there were no internal velocity at all, as if this 10K was nothing. Well, the 10K is always adding to the inertial behavior of the one constant component, and it changes everything as it should, create the equivalency that we're looking for. But here's the key thing that will come up very shortly. When we see this natural activity here of this vector being created, we see that it's actually having to travel at 22.36 kilometers per second along this path. Not 20, but yet a integration of 10 kilometers this way, north, and 20 kilometers east. We get what we should get is a resultant vector with a magnitude of 22.36. That balances everything. And though we have as a sense of things that 20 kilometers is meaningful from the point of view of the spring load, it still has to integrate. It has to deal with what are inertial components. And in dealing with the inertial components, we find it flying out, not straight away, but on an inertial path that is a vector. And just as an aside, after all of this calculation was done sort of directly under basic delineations that we use with these expressions, we looked at this and said, well, I wonder what a vector calculator would show us should be valid here. And this is what we get. We have the x velocity of 20, which is the native energy in the spring, and the 10 kilometers per second that is native to the frame. And we end up with a 22.36 magnitude and a 26.56 angle, which looks like this. And it's very suggestive of what we looked at in this case. The angle is exactly 26 here. So the beauty is this assay just comes to show that breaking it all down to make the analytical case, spatial case, all of these step through and sequences that just illustrated here in these just 2 pages of math, ending up with a magnitude of 22.36 for this inertial path that sort of ends up solving the whole case. We get 2 outbound projectiles dealing with their inertia in the system that they have to deal with, each one presenting its own element, and we get the outbound projectiles hitting at the same time after 0.4 of a second, and we see the returning projectiles returning to the same point, P1, that has now moved through space, but it is now the same collecting point 0.4 of a second later after the second cycles have gone through. Again, 3 different velocities are actually imputed here by this inertial case, and makes perfect sense. And just outside of our hard raw cranking, we go to an online calculator and get exactly the same data. It's as if this calculation understands exactly what we're trying to do when we spatialize it. That's what it looks like. That's what the calculations show us. Very interesting. And now for the important point I'd like to bring to bear, what I think we will have to sort of call the discontinuity in the case. We're going to do what we often do when we do this kind of analysis. We're going to have the 20 kilometers in the canon be the validating component for the same mathematics. In other words, it's going to go out at 20 kilometers per second as the element recedes, and it's going to return at 20 kilometers per second. Remember, not 30 and 10, but now 20 and 20. Now, we might have overlooked it as we were going through all the basic details, but we came over here and we saw that in the outbound path and return path on axis, we saw that each leg resulted in a total path of 16 kilometers divided by the 0.8 seconds. And we see the internal dynamic we kind of know to be true. We see a 20 kilometers per second as the average velocity under scrutiny, as if we could just lift out the idea of the 20 kilometers per in the canon and call it valid. But we can't. You see, this is, well, as we'll see, we can't. We can't because when we do and put the 20 kilometers in, we have actually now created, if you think about it, we have created a non-inertial case. And that's what these maths are going to show you. We are now looking, even though we've done what is normal, we are putting this now under scrutiny as the non-inertial case, because none of the velocities are going to change in this case. And in that case, when we do that, we see something very different we see that it takes the outbound tennis ball, it takes 60, it won't intercept the moving wall until it's achieved 16 kilometers downrange, or has moved 16 kilometers, which puts it at that point 16 kilometers downrange. But of course, the frame has moved in that same time, and it's down there. Its reflecting point is there as well. So that's what we see, and we see that takes 0.8 tenths of a second. Well, now, again, using the same key points of the same velocity, making this a non-inertial case, we see it return towards the moving frame, and it only takes 0.288 seconds to do that. Well, that's not equal to that, so we already know immediately it's not going to be similar to the Cartesian case we just looked at, because, again, we're seeing cycle times or activity times that are based on a demand that we use the average velocity that the cannon will make for the projectile. And we say, after we look closely at the previous case, this doesn't look like that case at all. This is showing something very bizarre. It's taken 8 tenths of a second to get one leg out, and 0.266 seconds for the second leg to occur. And the total time, instead of 8 tenths of a second as we looked at earlier, is 1.066 seconds. And guess what the average time is? The average velocity, of course, is 20 kilometers per second. So both scenarios create, and here we see it, 20 kilometers per second, the general average time. The total length divided by the total time gives us 20 kilometers per second. So, wow, we got the same average time, but a different contextual analysis. As you might guess, the next scenario is going to be even more interesting, where we try to analyze the cross-axis. Now, at this point, there's going to be a bit of insertion here. I'm just inserting this case right now. I'm going to say, well, I'm pretty sure that the cross-axis is now not going to, the cross-axis activity is not going to model the on-axis activity. I'm just guessing that from the fact that I get an 8/10 and a 2/10, two independent cycles, or two independent legs with different times, or that's what happened. Now, for the cross-axis, I have a puzzle. I'm pretty sure I can't get the cycle to have equal times, which has to be for the Galilean relativity. It can't do that. It can't have an 8/10 leg this way and a 2/10 leg this way and yet be equal. Do you see the simple point? So I know something's not going to be right here. Something is not squaring. So to the degree it is not squaring, we have to look at what's essentially a possibility. What's the possibility here? Well, one possibility is to get it back to the origin point at the same time. The cannon is now at 10.66 downrange, 10.66 kilometers downrange. And so this is the return point at 10.66. Well, half of that gives us a possibility to give us equal legs, but that's just not seemingly correct. Something's a bit wrong. And so just call that a disposable case for the exercise of Galilean relativity. It's not important. But now let's look at something that is important. And this is where we look closely at Michelson's mathematics. And we see that they are actually employing what we are just calling the non-inertial case, which sounds pretty good because light, as we would say, does not exhibit any inertial characteristics in terms of its velocity. It moves through things, it would move through the frame at one speed, right? Just like the 20 and 20 case earlier. C and C is what we would assume makes perfect sense. And so as we see it, though, we put our base numbers, our 10 and our 20, in Michelson's mathematics, this, as we looked at it earlier, 2L over large V divided by 1 minus small v divided by squared minus large V squared. Well, it computes exactly the same 1.066 seconds we did with the more rudimentary mathematical case. And so for its cycle time, for Michelson's cycle time, the on-axis completes a 1.66 second journey, 1.066 second journey. And we then use his math as it was projected in the page we looked at. We add the square root here, the radicands here, and it computes a final time of 0.923. So for the on-axis, we get a return to the base, as it were, the base of the frame, or the original cannon, or where the original cannon fire had come from on the frame. We get it at 10.67, but if we use his math, we have to chart a different course where 9.23 downrange is where it will hit, because this is, in this particular case, it's graphically interestingly linked in terms of powers of 10, but more importantly, we see that the reflection point then is not at the 5.33 we just threw out there for the test case. It is actually 4.615, and that's where it would be. In this case, we look at the spatialization of it. We see half of 9.23 is 4.615, and this all balances nicely. And we see that, in fact, it ends up with showing us a 20 kilometers per second activity along that path. And of course, we see the original problem that Michelson had to deal with, because he sees that this is going to be true in his mirror maze, and this is where on the y-axis he sees this gap, and on this axis is where he assumed he could push them back through the out to the collector along the y, and he would get his gap. You see, we've just established where his math is showing why there is a gap and what's meaningful about it. And we're wondering quite a bit how that's going to be valid, because in our next page, we have to ask, well, we still ask, what does vector analysis produce for us with 10 north and 20 east, which is still the numbers being put into here? And of course, we saw in the original case, it would still be the same case of 22.36 and 20.56 as the angle. Magnitude 22, angle 26. In other words, we see this original case where it was at 4 downrange, which turns out for us to be the 4/10 of a second we were looking for, and here. And so this is what the vector analysis produces. This is what Michelson's math shows us, 9.23, and then just the case for rudimentary partial Galilean return, at least at one point, not at both points, but just back to the say, we see this. So this is how all the math would work itself out under all these different conditions. And we still have to ask, which one of these, though, this orange dotted path or this dark solid green line, which is Michelson's path, which one of these is valid for the case? And that's where I'm trying to show a discontinuity. This is a very real discontinuity in the case. Michelson's math is, listen carefully, this is how we would say it, because this is what he's doing. He's putting non-inertial mathematical components into an inertial model. Did you hear that correctly? He is putting non-inertial components into an inertial model. And so he gets his assay then becomes that thing. He's expecting a thing that's not going to happen, because what's going to happen, or as a background to what is much more likely to happen, we should say that this is the normative case for that kind of assay, that inertial assay. But light, of course, is not inertial that way. There's the surprise. Light is not going to be inertial this way. It's not going to pick up, as we are assuming, the proper inertial activity of 10 north, as it were, and 300,000 east. You see, that's the component of what light would be doing under the scenario. It's not going to pick up any velocity, and so it can't be properly inertial. You see, it's trying to model an inertial case, but it's using a non-inertial mathematical dynamic. And that's the discontinuity I'm trying to show, helps the case I'm trying to make, which I hope makes some sense here. So just as a strong summary here, I hope that everyone can see that this case, just the form of it, is the inertial construct. That's the inertial construct. I just mentioned that Michelson is using non-inertial mathematical components in it. And so I think we should expect certain irregularities in his outcomes, and see that his assay has irregularities. That's what I'm hoping. But we should also then sort of say that, as such, the experiment may not go as he predicts. And so when we do the root of this, so when we look at the root of what Michelson's doing, this, we have to say, is a non-inertial mathematical input. The 20 and the 20, which is completely normal for almost all of us because it satisfies a time rate problem we all understand. It gives us an expectation, first of all, that is, well, it won't return to the same point at the same time. We get that. But for his math to have any value at all, it has to follow this path. That's where all of the time cycle is presumed to be occurring. It's on this path. Again, in his original case, it was non-reciprocated, and the ether was flowing by, and the photon was just fighting to go straight there and straight back, which is almost looking like the non-inertial case. But we see that the case in normal terms, as it were, you can't do that. In other words, we're saying you can't reciprocate it, though mathematically you can. But to see the truth, you have to not get the reciprocation out of it. That's part of the conclusion here. You got to get reciprocation out of it, though it does not seem to violate anything in Michelson's context. That's the big clincher here. Reciprocating it really doesn't do anything for the math, except that it masks what's going on until you take the reciprocation away and then ask, where does all this lateral inertia come from? You see? It goes on to be true, however, that if you put a photon on this path, it could travel exactly as Michelson predicts it. This is the confounder or the complexor in my case, is that you could put a photon right here and it would follow this Michelson's case exactly, because it would start here on this vector at C. It would happen to fit this particular frame dynamic. See, that's just the frame dynamic that this vector simply satisfies. That's the point. It's not a result of this frame dynamic. It's just we're putting the proper angle on it as it leaves the source, the origin, and travels at the one magnitude it can travel at which is C, and then all the rest of the frame catches up to its needs when it hits over here, and then it can reflect back on the normal. So there's a mathematical solution for Michelson, but again, it requires the imputation of lateral inertia to get it on this path. And at the same time, it can't pick up any of the dynamic from the frame itself. Do you see the break? Do you see the break as I see it? That's what has to happen for this case to resolve itself. And as I think we've seen already, it doesn't. Even though you could have the expectation of a gap there because of the motion, which is, admirable. Michelson was on the path of something real. The motion should create this gap. He really was trying to find the gap. But his non-inertial mathematical components, which seem to satisfy light, don't behave properly, as I guess we could say it, when you put them in an inertial construct. And again, as we saw it earlier, all the the proposition that I make is to make light non-inertial and not have any of this kind of behavior, but simply have the behavior where if you're looking at a splitter here, it only went out and back before the splitter got very far. See, these are dynamically large gaps here, but just imagine this going straight away non-inertially and straight back non-inertially, and hitting a splitter that has only moved so far in the real case of things. That's the many hours of discussion I've tried to make as I discussed the accommodation sequence, which is the solution that follows a true, and I guess that's the point here, a true non-inertial case doesn't even have this expectation of a path. That's the true non-inertial case. You can then actually kind of use the same elemental math, meaning C can be a constant in the analysis, but you have to look at it completely differently than when you try to cobble the non-inertial mathematics into an inertial template, which is, again, that's the only way to say it. You're looking for the non-inertial components to comport properly when they don't, because they're trying to be forced into an inertial template. And so when you see this angular detail here with this down and return of this, when you see these two together, you're looking at an inertial case by template. It's how you do the math that's everything. And again, for there to be true inertial components for this solution space, you're going to need 3 different velocities: one outbound, one returning on the on-axis, and then one completely different from those two on the cross-axis. And so that should be borne out by any deeper analysis of this. That's the discontinuity that seems to help my case seriously, because now I'm explaining it in somewhat non-opaque terms. We're saying it directly. Michelson is using an inertial template and then driving non-inertial mathematic complements through it, and it doesn't work. But to do his non-inertial case properly simply requires that you understand that a photon will not follow this path, especially because it doesn't have any lateral inertia. Nothing puts it on this path. As we said before, a thing could be put on this path from the emission point itself. In other words, if we were to put a great big flash at the instant all of this begins to go into motion, one of those rays coming from that flash will follow Michelson's path. But the one that should be of import is the one that goes straight away and straight back, bearing no inertial. That's the real honest signature of it all, is there's no inertial behavior in such a photon that goes straight there and straight back. It's going at C. So is this one, but it started on this path per se. And if this frame dynamic wasn't exactly right, it wouldn't get there to satisfy this. Do you see what I'm saying? It's on this path regardless of the activity on this frame. So that's the meaningful hidden component that seems to structurize Michelson's mathematics, but we see it for what it is if you get very serious about the spatial arrangement of all the details. And so, yes, there's a solution. You put a burst of radiation right here, there is one beam that would satisfy this case. In fact, it would be the only one for this case, you see? But nothing in Michelson's scenario of putting a source, let's say over here, to fire a beam this way, puts a photon on this path once it gets past the splitter. You see, there's the heart of the deep analysis. There is no putting it on a path like this once it gets through the splitter. Mathematically, there's a resolution, but it's not what we should expect. We should expect a true non-inertial behavior that comports with a true non-inertial analysis. So just to throw this in as we close out, we're going to look a little bit at how the proper case should be made for this, meaning what does a true non-inertial template look like for using non-inertial mathematical components? And it would look something like what's developed here in the last 10 minutes of this particular video. And importantly, we see that this is the key dynamic that I am working with when I say this is a true non-inertial case. The light came through and never left where the source put it on, the path that the source put it on. Yes, the source moved, and we say that then the source was merely entangled at this point in space when it loosed the emission point, and the emission point is the key to the whole outcome of a non-inertial case. But that's, again, what we've described in many other parts of this survey. This is what we need to look at as we close out this. This is what the final analysis looks like for a non-inertial, a true and complete non-inertial case. You see the one ray go out and back, which is very, very similar to the original case that Michelson presents for us, and then a cross axis which does not have any V activity in it at all. It goes out, it simply hits this other mirror, not, let's say, at the dead center focus that would be here, but we just accept that the mirror just slid on by a little bit. It hit at a different point and then returned. That's why the requirement is these have to be at 90 degrees before the test begins. And you have to certify that without using the mirror, because all Michelson did was tune these mirrors to make one point happen here, which is easy to do. We're saying start with 90 degrees and you end up with this kind of dynamic. And it's non-inertial all the way through. C is maintained all the way through, and you get an outcome where there is the gap Michelson was expecting. His assay was not wrong in the one regard, or his deep logic was not wrong, because the deep logic is the Earth is moving at its one velocity and light is moving through the frame of space at one velocity. Those two should, in some case, like this mirror maze, produce some result that should show those two different activities even as the light cycles through that mirror maze. And this is how it would look. It would look like a gap here, not on X, as we keep saying, not on Y. And there you go. This is the root of the argument. This is the root of the non-inertial case. I say anyone at Michelson's time should have been able to consider this too. This is not something modern or new. This should have been in 1887, 1 month after Michelson reported his failed experiment. And so this concept should have been in direct competition with Fitzgerald's offering. Fitzgerald just fixing Michelson's overall assay. And what should have just, and he, of course, as we know, he invented a whole new empirical phenomena to match Michelson's flawed structure. That's how I would say it at this point. And correcting Michelson's mirror maze is almost is trivial. It's actually trivial. All you have to do is understand you need to start with mirrors that are at 90 degrees with one another and a splitter that's at 45. And you will get what you want if you understand that there should be a gap. You will get that gap due to the velocity of the Earth. Oh, and more importantly, this would reveal all motions incumbent on light in this scenario. So if we were just looking for a gap that reflected 30 kilometers per second, it may show a much greater velocity, and or because this is astronomically valid, it may show less velocity than we might expect under other scenarios. And so what Michelson was trying to do was create a research tool so that an experimenter, an observer, an astronomer could take the motion of Earth out of his calculations. And we're saying this is actually how you do it. You can find the velocity of Earth and maybe all the other motions, but now all astronomical values are true, because in Michelson's original case, he thought rotating the platform on which the mirror maze was sitting would give him all these various data points at different times of the day, well, not so much every time of the day, but, well, yeah, at different times of the day, but more meaningful at different times of the year. Charting everything every day for a year was going to give him his complete data set that he was looking for to begin parsing other anomalies out. And that would be true for this particular corrected interferometer. You correct the interferometer and you can do exactly what Michelson wanted to do, which is do research based on the astronomical configuration of all things around and all of their relative motions. In other words, what we're saying here is sadly in conflict with all the later analysis, which is we can go back to Newton's idea that space, maybe not ever calling it absolute, we can call it substantially fixed or substantially rooted. Because the reason you are not where I am and I am not where you, because we are two different points in real space, substantial space. And this analysis is only asking you to consider that space is substantial. The different points in it are substantial. They're not mathematical incoherencies that come from relative rest, which is the whole case we've tried to make along other ways. This is the accommodation sequence built on a true corrected non-inertial case and template. See, this is a non-inertial template. The frame is moving. The light source moving at C doesn't have any component of lateral inertia. As we know, we would know that's where every star is. If the light that was released from them stayed lateral to them as they moved along, well, then every point of light would point directly to where every star is now. But see, we know it doesn't. The light comes at us, starlight comes at us on a different angle, as it were, than where a line drawn to where that star is right now would be, because they separated in space, substantial space. At the instant the emission occurred, the two items were entangled in space, and instantly after that, they separated and went their own ways. The frame went that way, this way, the other way, whatever velocity it's going, and the emitted light found its one vector going straight away to parts whatever on its own vector, its own angle, and the light, if you ever reflected it straight back on its path, it would go straight back through that emission point in our substantial space argument, and not somehow, who would know how, it would not find its way back to the source. The only way it could find its way back to the source properly is to reverse time, which seems to be part of the speculation of a lot of thinking, which I don't know how to address. So there it is. The critique here is just topical, but I think meaningful. And it does at least help. The case I'm trying to make is that Michelson's cross-axis assay was flawed more so than his on-axis assay. It helps us if we take the unreciprocated case. We see that we have to assume some sort of lateral inertia, but that lateral inertia would then impart some of its frame's inertia to it to put it on that path. So the lateral inertia case just fails. You can't add speed to light. You can deflect it, and that's presumably what's happening. But the deeper drawn case says no, he's trying to put non-inertial components in an inertial template. And that's the discontinuity in his case, in his assay. Correcting that, it's trivial. It's trivial to the degree all you have to do is get 90-degree angles before you start, and that's possible to these days, and then a splitter that's at 45 to them, and then now just assume, as it were, that the motion of the Earth is going to satisfy the original condition. The original condition is the motions along these two paths will do something. In other words, it's foundationally analytically true that the two motions will reveal some differential based on this particular test. It's just that we see that the differential looks like this. It looks like this on the x path. So this is the correction for Michelson. Not a big theory. This is just an analytical correction. And this is what it would look like. And this is what you should expect. Propose is the true and proper non-inertial case. whereby Michelson's original case has something like this trying to go on with these maths, and then of course in the static way of looking at it, it doesn't reveal itself until you spatialize. See, this is the static argument, and you just look at it mathematically. Or this is a static graphic that you look at mathematically, and you think, "Oh, this is going on," and okay, well, we get it. We get two different outcomes coming out of here to go to head down Y to the frame to the collector. And again, we're looking at excerpts from Michelson's error, a video document that sort of tries to isolate all of these points very carefully. And we see Michelson's original argument presented in this V of activity that, again, we just don't know where this lateral inertia comes from without altering the velocity of the entity that's being altered supposedly by the inertia of the frame, or supposedly by this model. It should be altered by the inertia of the frame. And we just find that not satisfactory, especially when such an obvious and clean non-inertial case presents itself. But we just looked at it. And so there's the telling of the tape for Michelson. We see him trying to put a non-inertial complement mathematically into an inertial template, and it just doesn't. This doesn't bear fruit for Michelson until Fitzgerald invents a whole new paradigm in physics of a thing called shrinkage along the axis of motion. Thank you.